So, in this class we are continuing from the last lecture, where we were checking the variation in the parameters, the effect of the changes in the parameters on the optimal solution. So, we were talking about the changes in the coefficient matrix, that is A. The first part we have done, that is if A k does not belongs to B. In this case, we have observed that if it lies in this range, in that case there will be no change in the optimal solution. Now, let us see the second part, that is whenever your A k lies between A k belongs to B, that is your case 2. Case 2 is when your A k belongs to B. So, in this case, since A k belongs to B and x b equals B inverse B, so it may happen, two cases may arise. One case is feasibility remains unchanged, and second case is feasibility will be changing. So, feasibility is unchanged. Two cases I may say, that is feasibility is unchanged and number 2, the optimality is unchanged. So, whenever A k belongs to B, since x b equals B inverse B, your feasibility may be changed. So, once the optimal solution or feasibility is changing, so what we will try to check that for what range, for what variation feasibility will remain unchanged, and for what variation of A k your optimality will remain unchanged. So, that is our basic criteria, because otherwise again we have to recalculate the problem. So, the first case, let us come. Suppose your B is B1, B2, Bm. B1 is B2, Bm, Bm, where Bj belongs to A. I am just writing once here, j equals 1 to m, and your B inverse we are assuming as beta 1, beta 2, like this way, say beta m, where beta j is nothing but the jth column vector of B inverse. Beta j is the jth column vector of B inverse. Now, since your A k belongs to B, we are doing this case. So, if I make a change in A or k, what it will affect? It will affect kth column of B. It will affect the kth column of B. So, there will be a change from B to B star. So, I can write down there will be a change from B to B star, and B star I can write it as B1, B2, like this way, B k minus 1, say B k star, B k plus 1, and like this way B m. So, this vector can be written as a linear combination of the basic vectors of B. This entire vector can be written as this one, this B k star. So, B k star I can write it as a linear combination of others, that is lambda 1 B 1 plus lambda 2 B 2 plus lambda m B m, which is equals to, I can write down nothing but B into lambda, where your lambda is equals to lambda 1, lambda 2, and like this way lambda m. So, since B k star equals B into lambda, so I can find out the value, or I can write down the value of lambda as from the earlier equation B inverse into B k star. B inverse into B k star, and what is B k star? B k star I can write down B k plus this vector, in the kth place it will be delta A R k, like that way it is going to 0. So, it is nothing but B inverse B k plus beta k into delta A R k, where again beta k is the kth column vector of B inverse. So, B inverse B k is nothing but the E k plus beta k into delta A R k, where your E k you can write down, E k is nothing but summation over I equals 1 to m beta I into B I k. So, this is equals B inverse into B k. So, basically E k is nothing but the unit vector whose kth element is 0 1 and others are 0. It is the unit vector whose kth element will be 1 and others are 0. Now, for feasibility condition, your value of x b star should be greater than equals 0. That is, for feasibility condition, your x b star, which is nothing but b star inverse into b, this should be greater than equals 0. Now, when b star will be b star inverse, this one b star inverse, this will exist only when b star is non-singular. As we know, if b star is non-singular, then only b star inverse will be existing. So, we must have this delta k should be not equals to 0. Now, from the earlier one, that is from b k star equals this thing, from b k star equals b lambda, from here you can write down lambda k b k, lambda k into b k, sorry, before that b k star, this is equals lambda 1 b 1, lambda 2 b 2, like this way, lambda m into b m. So, once I am writing this, this implies lambda k b k, this is nothing but minus lambda 1 b 1 minus lambda 2 b 2, like this way it is going, plus b k star, and the last one will be minus lambda m into b m, which implies your b k will be minus lambda 1 by lambda k into b 1 minus lambda 2 into lambda k into b 2, like this way, plus 1 by lambda k into b k star, and like this way minus lambda m by lambda k into b m. And please note that here your lambda k star is not equals to 0. Your lambda k star, lambda k is not equals 0. From this we have told, since b star is non-singular, so we can write down this. Therefore, once I obtain this b k, so x b star I can rewrite like this way, your x b I star, this equals, I can write down x b I minus lambda I by lambda k into x b k. Two things will come. This will come whenever I is not equals to k, and the second one will be 1 by lambda k into x into b k, where when I equals k and of course, lambda k is not equals to 0. So, x b star we are writing like this, but what is your lambda k? Your lambda k equals, I can write down 1 plus beta k into delta A R k, whenever I equals k, and your lambda I equals beta I k. From here I can write down beta I k into delta A R k, whenever I is not equals to k. So, that you can write down your x b I star, this is equals to x b I minus beta I k delta A R k, from here, from this calculation, divided by 1 plus beta I k delta A R k into x b k, I is not equals to k, and it will be x b k divided by this 1 plus beta k k, this will be beta k k into delta a r k when I equals to k. So, I obtained this thing. Now, for feasibility, what happens? We know that for feasible solution, your x b star always should be greater than equals 0. So, therefore, this quantity should be greater than equals 0, or in other sense, you can write down x b I into 1 plus beta k k delta a r k minus beta I k into delta a r k x b k, this is greater than equals 0, which implies that this quantity is greater than equals x b I can go on that side. So, from here simple manipulation, I can write down delta a r k should be greater than equals minus x b k divided by beta k k x b I minus beta I k into x b k, and whenever this quantity is greater than 0. And similarly, delta a r k will be less than equals minus x b I divided by beta k k x b I minus beta I k into x b k. If I assume that this value as equals to capital L, so I can tell it as capital L, which should be less than 0. So, I am assuming the denominator as same, the denominator will be same. So, delta r k greater than equals 0, delta r k less than equals 0. So, from here for feasibility, I may say that I can write down maximum of minus of x b k by this L, where L is greater than 0, less than equals delta a r k less than equals minimum of minus x b I by L, which is less than 0, where your L is nothing but beta k k x b I minus beta I k into x b k. So, we may say that if the old solution has to be remain unchanged, then the variation in the for feasibility, the old solution will remain feasible if the variation lies in this range. So, I can simply check whether the variation on the coefficient matrix whatever I have made, if the variation lies in this particular range, in that case I do not have to recompute the problem, I can tell that old solution will remain feasible. Now, I have to check the optimality. For obtaining optimality, what I have to find out? We know it that for optimality this condition must be satisfied, z j minus c j must be greater than equals 0. Now, for changes, z has changed to j star say, so it will be equals to c b b inverse a j minus c j, and which is equals, you may write down summation I not equals to k to m c b I y I j star, it will change minus c j, where your y I j star I can write down y I j minus delta a r k into beta r k divided by 1 plus beta k k. This again from this calculation, just like we did the earlier calculation. On the similar way, if you do the calculation, since it is similar type, so I am not showing the entire calculation. I not equals k, and this will be y k j divided by 1 plus beta k k into delta a r k whenever I equals k. Your y j star will become this one. Now, z j minus c j or z j star minus c j then will become z j star minus c j will then become z j minus c j minus y k j delta a r k c b into beta k divided by 1 plus, from here I am getting it, 1 plus beta k k into delta a r k. So, once I am getting z j star minus this, and for optimality your z j minus c j star, this quantity is greater than equals 0, or in other sense this one z j minus c j into delta r k, this should be greater than equals 0, implies your z j minus c j plus delta a r k into z j minus c j into beta k k from that itself minus y k j c b into beta k, this has to be greater than equals 0. Now, if you assume this quantity is equals to say theta j. So, if theta j greater than 0, in that case delta a r k is greater than equals minus z j by c j by theta j, and if your theta j is less than 0, then delta a r k will be less than equals minus z j minus c j by theta j. So, from these two combine, if we combine these two, then we will obtain maximum of minus z j minus c j by theta j, where theta j is greater than 0, less than equals delta a r k less than equals minimum of minus z j minus c j by theta j, where theta j has to be less than 0. Therefore, to maintain the optimality, if the variation in the cost in the coefficient matrix A, if it lies in the given range whatever we have given, then the old solution will remain unchanged. So, basically what we have seen for the coefficient matrix capital A, if there is a change or variation in the coefficient matrix A, the feasibility and the optimality may change. So, here we have derived one conditions for which the feasibility and optimality will remain unchanged if the variation lines, if the variations lies in the range provided here, then the feasibility condition and optimality condition both will remain unchanged. So, these are the three variations in three parameters, that is C, B, and the next one was A. Now, we will go to the other one, that is addition of a variable. Suppose a variable is added, say x n plus 1 with the cost component C n plus 1, then the reformulated LPP can be written as maximize z equals C x plus C n plus 1 plus x n plus 1, C n plus 1 into x n plus 1. One variable is added. Earlier there was n variables x 1 to x n, now I have added x n plus 1. So, cost coefficient is this. Once I am doing this, your A will be changed to one more coefficient will come here. So, in place of A, the matrix will be A comma A n plus 1, and your decision vector x will be changed to x and x n plus 1 will be there, B will be changing. Obviously, x greater than equals 0 and x n also plus 1 greater than equals 0. Now, for optimality, your Zn plus 1 minus Cn plus 1 should be greater than 0 and Zj minus Cj is already satisfied. Your Zj minus Cj is already satisfied for the old problem. Along with that, for optimality, your Zn plus 1 minus Cn plus 1 also should be greater than 0. Therefore, if your Zn plus 1 minus Cn plus 1 is greater than 0, old solution is optimal, because there is no change automatically. This is also satisfying the optimality condition, new variable, and if B star is the optimal solution of the original problem, then B star will also be the basic feasible solution of the new problem. So, you see, if Zn plus 1 minus Cn plus 1 greater than 0, then old solution will remain the optimal solution of the new problem also. This is because since the new variable is non-basic initially at the 0 level. Now, say when Zn plus 1 minus Cn plus 1 equals to Cb into B inverse An plus 1 minus Cn minus 1. So, Zn plus 1 I am writing this Cb B inverse An minus Cn plus 1. If it is less than 0, then we have to find out yn plus 1 equals B inverse An plus 1, and in that case I have to proceed with simplex method, so that An plus 1 entered into the basic. Or in other sense, if Zn plus 1 minus Cn plus 1 less than equals 0, then I have to reformulate the problem. Please note this one. We have to reformulate the problem and we have to use the simplex algorithm to obtain the solution. So, if I have added a new variable xn plus 1 and if the coefficient of the new variable xn plus 1 is Cn plus 1, and if I find Zn plus 1 minus Cn plus 1 is greater than 0, then the optimal solution of the old problem will remain the solution, optimal solution of the new problem. But if Zn plus 1 minus Cn plus 1 is less than 0, in that case I have to reformulate the problem, I have to generate the new initial basic feasible solution, and I have to use the simplex method to solve the problem. And the last one is, if I want to add some constraints, that is addition of some constraint. Now, whenever you are including some new constraint, the new constraint may or may not affect the feasibility of the current optimal solution. Please note this one, that the inclusion of the new constraint may or may not affect the feasibility of the current optimal solution. First, to check current optimal solution satisfies the new constraint or not. So, basically at first you are checking whatever optimal solution you have obtained for the old problem, after adding the new constraint, whether that optimal solution is satisfying the new constraint or not. If the new constraint is not satisfied, if the new constraint is satisfying the current optimal solution, then present solution is feasible and that solution will give you the optimum solution. Means in that case you do not have to compute. But if the new constraint is not satisfied by the present solution, then your current optimal solution will become infeasible. So, in that case we can use the dual simplex or some other problems to obtain the optimal solution, that we will see. So, in other sense, whenever I am adding a constraint, in that case if the new constraint is satisfied by the optimal solution, by the feasible solution, then the old solution will remain the solution of the new problem itself. But if the new constraint is not satisfying the present solution, in that case your current solution or solution of the old problem will not be feasible. So, I have to reformulate the problem and I have to do this. So, now let us take one example and see how it affects the other parts of the problem. Just presenting the problem first. We will discuss the solution of this problem in the next class obviously. Just I am discussing the problem. A company wants to produce 3 products X, Y and Z. The unit profit of these products are rupees 3, rupees 5 and rupees 4 respectively. So, unit price of each of the products, for product X it is rupees 3, for product Y it is rupees 5 and for product Z it is rupees 4. So, basically I am producing 3 products and the quantity of products are X, Y and Z respectively. So, my objective is to maximize which one, 3x plus 5y plus 4z or x1, x2, x3. If I am producing x1 quantity of x, if I am producing, here I have written, if I am producing x1 is the number of units of product of x, x2 is the number of units of product of y and x3 is the number of units of product of z. So, in this case my problem will be I have to maximize 3 into x1s because unit profit for product 1 is 3. Similarly, 3x1 plus 5 into x2 plus 4 into x3 I have to maximize. These products has requires the 2 type of resources, manpower and raw material. What is the manpower restriction? I am saying x1 plus x2 plus x3 less than equals 4 and raw material restriction is x1 plus 4x2 plus 7x3 less than equals 9. So, my problem is this one. What I want to find out? We will solve 5 different problems for this. First one we will find out the optimal solution of the LPP. Next we will see the range of profit contribution of x and z in the objective function such that the current optimal product means remains unchanged. That is how much variation I can make in x and z, so that current solution will remain the solution even if I have made changes in x and z. Then number C, what shall be the new optimal product mix when profit per unit for product is rupees 13. That is, whenever I am changing a coefficient. Then discuss the effect of change of availability of resource from 49 to 94. That is, whenever you are changing the matrix B, what happens and which resources should be increased or decreased to get best marginal increase of the objective function. Or in other sense, the theory which we have discussed in this lecture and the earlier lecture, how to implement those theories, that we will see in the next class.